So, to kick off our deep dive today, let's maybe talk about something unseen, precision. Have you ever wondered what makes the most critical parts in our world?
Mm.
From engine components to high-precision instruments, incredibly strong, really smooth, and, well, perfectly shaped.
Yeah, often it's something you never actually see happening.
Exactly. And today, we're taking a deep dive into CNC cylindrical grinding. I mean, this isn't just a small step up. It feels more like a fundamental shift in how we approach finishing work for really critical components.
That's precisely it. And our mission here really is to unpack why this specific technology delivers such unmatched precision, that amazing surface finish, and crucial material integrity.
Right.
We want to explore what that really means for parts that simply have to perform flawlessly and last a long, long time. And how does a spinning wheel essentially become so revolutionary?
Okay, so we hear a lot about precision machining in general. But what makes CNC cylindrical grinding the ideal choice when you need that super high precision and you need to ensure surface integrity? Because standard machining, I guess, it must leave tiny flaws, right? Things that could cause failures later on.
Absolutely. And what's really fascinating here is how the CNC part, the computer control, it automates everything to achieve this extreme dimensional accuracy. Think back, manual grinding was so dependent on the operator's skill, lots of variability.
Wow.
And CNC just removes that variable, gives you consistent microscopic precision, but it's more than just accuracy. Critically, it preserves the surface integrity because it minimizes heat buildup.
That's a key point, the heat.
Huge point. So you get parts that aren't just the right size and shape, but they're intrinsically strong, they're reliable right down at the surface level.
Huh.
It really is a paradigm shift in finishing. Solves a lot of problems at once, and it works for, tiny workshops or massive production lines.
So it's not just about the shape, it's making sure the surface of that shape is strong, almost at a molecular level.
Interesting. So given that, where does this unseen perfection really make the biggest difference? What kinds of parts, what shapes really need this?
Well, if you've ever tried to get something perfectly, truly perfectly round, like shafts for aerospace or maybe tiny pins for medical devices, you know how tricky that can be.
How about
Yeah, standard methods can leave you with tiny amounts of runout or taper you might not even see, but they matter. CNC cylindrical grinding just excels there. It's not just finishing the outside, the OD, or the inside, the ID of cylinders. It delivers this geometric accuracy that honestly was just a dream not that long ago.
So when it comes to round things, it's basically the undisputed champion. Is there like any situation with a round part where maybe it's overkill? Or maybe another method is just faster or cheaper for, say, high volume? Good question. For the absolute top tier of precision and surface integrity, yes, it's the king. But yeah, you're right. For like a simple washer that just needs a hole punched in it, no, you wouldn't use this. It's overkill.
Right.
The real magic is its versatility for precision round parts. So external surfaces, think shafts, pistons, pins, rollers, you get perfect roundness, straightness, diameter control, critical stuff.
Huh.
Then internal surfaces like inside bearings, bushings, cylinders, achieving those exact internal diameters means components fit together perfectly. No slop, no friction issues down the line.
And tapers, you mentioned those earlier.
Yes, that's another game changer. Tapered parts like machine tool spindles or maybe valve seats. Getting that precise angle ensures perfect contact across the whole surface. Hugely important for how they function.
Wow.
And even really complex shapes, not just simple cylinders or cones, things like camshafts or eccentric shafts. The CNC can be programmed to follow these really intricate profiles again and again with incredible accuracy. Stuff that would be basically impossible to get consistent manually.
Okay. So yeah, less suited for blocky prismatic parts, that's usually milling. But if it needs to be perfectly round and the surface on that round part needs to be perfect, grinding is the way to go.
That level of detail is pretty incredible. And if we're talking perfect surfaces, what kind of finish are we actually talking about? Can you feel the difference, or is it more like a mirror?
Oh, we're definitely talking ultra fine. CNC cylindrical grinding consistently gets you finishes down in the 0.2 to 0.8 micrometer range.
Raw.
Roughness average. It's a standard measure of surface texture. And yeah, 0.2 to 0.8 is already incredibly smooth, but it can go even finer. You get this near mirror finish sometimes. Really ideal for anything where friction is the enemy or you need super high performance.
Okay, so getting that kind of finish isn't just automatic, right? You said it involves controlling, what, 3 areas?
Exactly. It's not just set it and forget it. You have to meticulously control 3 interconnected things. First, the grinding wheel itself.
Wheel beam. Yeah, it's not just any wheel. The grain size has to be incredibly fine for a super fine finish, but also the hardness of the wheel matters. And the type of abrasive material you use, different things for steel versus, say, aluminum or carbides.
Like aluminum oxide or silicon carbide.
Precisely. Using the wrong wheel is, well, it's like trying to sand a delicate piece of wood with a really coarse rock. It just won't work right. Even a tiny flaw on that wheel, if you don't manage it, can mess up hundreds of parts.
Right, leads to rejects, potential weaknesses you can't even see.
Exactly. Then second, you have to keep that wheel perfect. That's called dressing the wheel.
Dressing.
Yeah. See, as the wheel grinds, it picks up tiny bits of material, it gets clogged, and it wears down, but not always evenly. So dressing uses a diamond tool to kind of clean it off and reach through the surface, make sure it's perfectly round, perfectly sharp again.
Oh, okay. Like sharpening a knife, but for a grinding wheel.
Kind of, yeah. And doing that dressing consistently is absolutely vital. If you don't, the finish you get will change from part to part because the wheel's surface isn't consistent.
Makes sense. Consistency in, consistency out.
You got it. And the third piece is controlling the process itself. This is where the CNC really shines. It lets you control with incredible precision the rotational speed of the wheel, the speed the workpiece is turning, how fast the wheel feeds into the part.
It's like a complex dance.
It really is perfectly choreographed. And generally, a slower, more controlled grind with the right coolant washing away heat and debris, that always gives you a better finish than trying to rush the job. It's about managing the energy right at that cutting point, microscopically.
That makes total sense.
Yeah.
Precision across the board leads to a precise result. Which makes me wonder, how does all that control help with something notoriously difficult, like getting tapers or angles exactly right? Wasn't that considered kind of an art form back in the day? Super dependent on the machinist's skill.
Oh, it absolutely was an art form. Highly skilled work, but, prone to human error, inconsistencies between operator, even inconsistencies from the same operator day to day. Manual setups were tricky. CNC just completely changed the game for tapers. Now you can churn out hundreds, thousands of tapered parts that are functionally identical. Think machine spindles, valve seats, where that angle is absolutely critical for sealing or alignment.
So how does the CNC actually do that so precisely?
Well, the system is programmed with the exact angle and the path the grinding wheel needs to take. Then it executes those movements perfectly, often by swiveling the work table that holds the part, or maybe the wheel head itself, and coordinating all the machine's axes simultaneously. That automated control just gives you a consistency you could never, ever match by hand.
Okay, but what about things like the wheel wearing down slightly over time? Does that affect the angle on the 100th part compared to the first?
Great question. That's where the really clever part comes in. Many modern grinders use what's called a closed-loop system.
Closed loop?
Yeah, think of it like this. There's often a probe, a measuring device, built right into the machine. It measures the part, sometimes during the grinding cycle or right after.
It measures it while it's grinding.
Sometimes, yeah, or immediately after a pass.
Yeah.
That measurement data gets fed instantly back to the CNC controller, and the controller then automatically makes these tiny, tiny adjustments to the grinding path. It can even compensate for that microscopic wheel wear you just mentioned.
Wow.
So it guarantees that every single part, from the first one off the line to the very last one, meets the exact same specification, all without anyone needing to manually intervene. It's like hyper-precise self-correction.
That self-correction capability is just astounding.
Yeah.
It's not just grinding. It's genuinely smart grinding.
Which I suppose brings us to maybe the most critical benefit, especially for parts under huge stress like in engines or aerospace components. Why is CNC cylindrical grinding so vital for surface integrity and making parts resistant to fatigue?
Yeah, this really is the payoff, I think. For any part that has to endure high stress or cyclic loading, this is huge, because often how long a part lasts isn't determined by its overall brute strength, but by the quality of its surface.
Really, the surface is that critical. Absolutely. And CNC grinding helps in three main ways here. First, it actively removes surface defects. Think about other processes like turning or milling. Even if they look smooth, they can leave microscopic tool marks, tiny tears, or residual stresses.
Yeah.
These act as stress risers. They're like little invisible notches where cracks love to start when the part is stressed repeatedly. Grinding literally erases those flaws. It leaves a uniform, smooth surface without those built-in weak spots.
So it's not just making it smooth for low friction.
Yeah.
It's actively getting rid of potential failure points. That's a big deal for longevity.
It's a huge deal. It basically turns a potential flaw into a featureless, strong surface. Second, as we touched on, it minimizes heat. Grinding removes material as these incredibly fine microscopic chips.
Right, keeping the part cool.
Exactly. And that's critical because too much heat, even localized heat right at the surface, can actually change the metal's internal structure just beneath the surface. It can make it brittle or soften it in ways you don't want. By keeping it cool, grinding preserves the material's intended strength and microstructure right up to the surface.
Okay, so removing flaws and avoiding heat damage. What's the third way?
The third one is really fascinating. The grinding process, when controlled correctly, can actually induce compressive stress into the surface layer.
Compressive stress, like it squeezes the surface together.
Exactly. Think of it as preloading the surface, putting it into a state of being squeezed. Now, remember that fatigue cracks typically only grow under tension when the material is being pulled apart.
Right.
So if you have this built-in compressive layer right at the surface, it actively pushes back against any tensile forces trying to open up a crack. It makes the part dramatically more resistant to fatigue failure.
Whoa. So it's like giving the part a protective shield against cracks starting.
That's a great way to put it. A built-in force field, almost.
Yeah.
It can massively extend the working life of parts in really demanding applications. And think turbine blades, crankshafts, landing gear components, places where failure is just not an option.
Incredible. Okay, to kind of wrap up our deep dive today, CNC cylindrical grinding isn't just about making things round. It delivers this really unmatched combination of precision, exceptional surface finish, and fundamentally enhanced material integrity. It seems like it's truly the gold standard process for creating those critical high-performance parts, the ones built not just to work, but to work flawlessly and last much, much longer.
Absolutely. It's about creating components you can truly rely on, especially under demanding conditions. So maybe the next time you see a really complex machine working perfectly, or you think about a component enduring immense stress, consider that unseen perfection just beneath the surface. And maybe ask yourself, how might understanding this level of material integrity, this idea that microscopic surface details dictate the macroscopic performance and lifespan, how might that change how we design, how we build, and maybe even how we trust the machines all around us?